going to start the class. First, I would like to apologize that I wasn't here last Friday. I had an urgent meeting to go to, and so I'm here. Any questions regarding the course? No? No problem? Okay. So, today I'm going to sort of switch gear and talk about pack learning and empirical risk minimization, regarding empirical risk minimization. So, it's a little bit more mathematical than my first lecture, but I hope, please ask questions, okay? So, this, by the way, comes from the textbook, Understanding Machine Learning. It's chapter 2 through 4, okay? So, if you need, if you want to read upon it, please do so. Okay, and let me just very quickly go over the notations here. So we are given data and label, okay, and we call that domain space, and we call that Z, okay. So Z is equal to the product space of the data and label. This is the notation that we use, okay. So data, as I said, weight and height. This is the weight and height, and Y will be whether it's male or female. Okay, it's 1 or 0. S would represent the training set. This slash would represent the instance in the training set, okay? S, usually I can write it like this. This is the notation that I used in my first lecture. 1 through N, this N training set, okay? Data and label. And here, this is, I'm talking about just this right here, okay? The instances, okay? And I'm assuming, okay, and I'll get to this, and I have different assumptions about Y, okay? D will be the data distribution, okay? This data distribution may be over only the data, or it may be over the data and the target label. Okay, it's a distribution of data and label. F theta is the predictor or the hypothesis parameterized by theta. F is some ground truth label. Okay. LS, training loss. LDF is the test loss with respect to X and some fixed known D, F, unknown F. LD is with respect to the distribution of the product space of X and Y. H is the hypothesis class, which I mentioned. I'm going to be talking about what the bad hypothesis class is. Delta here is the probability of getting non-representative samples. So I have a training set, and I may get training sets that does not represent the distribution of, it's a non-representative. Okay, you want, let's say, the distribution of the data looks like this. You would probably want a lot of data here and little data here, if this is right. But if it's non-representative, most of my data are like here. This will be sort of a non-representative. This will be the distribution. I'll be going over this, okay? That's the probability of getting the non-representative samples. 1 minus d is the confidence parameter, epsilon parameter, and so forth. Don't worry if you're getting confused with this. I'm just going over the notations so that it will help you with what's going to follow next, okay? Epsilon is the accuracy parameter. You don't have to write this down. It's all in the lecture note, okay? LS is the loss with respect to S. What is S? The training set, okay? Training set. How many training sets do I have in this case? M. It's the average loss. So this is your predictor. It takes the X, training sample XI, it predicts a label for that, and it compares it with YI and see whether it is the same or not. If it's not, it gets the value 1. If it is, if it's the same, it gets 0. Right? And I'm taking the average over the training set. And so this is the training loss, LS. S is the training set. LD, this is just notation. It's the expected loss. I've defined this in my first lecture. The expected loss, or the expected probability. It's the probability that your predictor would not be the same with ground truth. That's the probability that it's not going to be the same. Your predictor. Your predictor is what? Is F. And you put in your X. And that value is not equal to ground truth. It's the probability of that. Over the distribution. Over the distribution of the data. Here in the data, I'm assuming X and Y together. Joint probability, joint distribution. Okay? LDF, in this case, it's similarly defined, but it's only over the data, the X. Okay? So if you, and here in this case, I'm assuming that the label is assigned by the function f. Okay? Now, I'm just going through the notation. You may say, what the hell am I talking about? So, just want to put this thing, give it to you, and I'm going to go over it again. Okay, first thing that you have to know is empirical risk minimization. ERM. Simply said, it's the function or it's the hypothesis that minimizes the training loss. Okay? You may say, what the hell am I talking about? Remember what the hypothesis space is? Hypothesis space contains lots of functions that you're going to consider, right? And I'm going to evaluate that each of those functions over all the training set. And I want to pick out the function that minimizes the training loss. So I have, let's say I have two functions in my hypothesis space. I have my training set. I'm going to use each one, and I'm going to get my training loss. Each function is going to be a predictor, and it's going to compare with the ground truth label. And I'm going to compare one, because I have two. I'm going to compare, and ERM chooses the function that minimizes the training loss. Okay, simple enough. ERM is a hypothesis that minimizes the training loss. And, okay. Now, some comments. Okay, this notation. So, the the hypothesis space that we're considering is all the function, it's some function that's parameterized by theta. What do I mean by that? Let's say it's a linear function. This bag, this hypothesis space, contains linear functions. So what is theta? It's the gradient and the y-intercept. Right? That's the theta. That's inside this bag. Okay? So that's theta will be the gradient and y-intercept. Okay? That's the hypothesis space. And I'm going to figure out the training loss over training loss, and I'm going to use all the functions available in the hypothesis, and I'm going to pick one that's minimizing the loss. And I'm going to call that Fs. Fs, meaning that for sample S, sample set S, remember what S, I said S was the set of training set. How many? M number of them, okay? So S can be written like that, right? Data and label. X, for now, I'm going to assume that only the X is a random variable. X is only the random variable that follows distribution D. Okay, here. And yi, the label, is just the output of some deterministic function. Okay? That's one way of looking at it. One way. Another way is assuming that both of them follow some distribution. Two situations. Okay? Understanding that there are two situations. One situation, we'll call this, we'll treat that a little bit differently. Okay? So I just want to say there's two situations. Usually for classification, the loss that's used for training loss is the 0-1 loss. What is a 0-1 loss? I defined this there. I don't want to say this. I'm just going to mention it one more time. Let's see. A. It's either 1 or 0 if A is true and false. If A is false. Okay, this is the 0-1 loss. So it's 0-1. If this is true, if it's not equal, then it gets the value 1, otherwise it gets 0. Okay, that's just comment. Additional comments. In my first lecture, in machine learning, there's inductive bias. What is inductive bias? Machine learning is not all about just using training data and getting some function. You have to make some assumption about the task before you look at the data. Huh? So for that task, you think it's going to be this or that. That's what we call inductive bias. Okay? So here, H represents the inductive bias, the hypothesis space. Oh, I'm just, for this function, for this task, I think only linear function is going to be good. I think it's only be quadratic. I think deep learning will be good of certain architecture. Okay? That's the inductive bias. And we may want to do this. This is what we're trying to do something in this lecture. This is the type of thing that you should know. Given 1 minus d, 1 minus delta, we call that, as I said, confidence, epsilon, accuracy. And these values are between 0 and 1. I hope you understand. When I write it like this, I mean that this means that it's a value between 0 to 1. So 0.1, 0.2, 0.3. Yeah? I hope you everyone, because there are some people who are not familiar with this type. And this is the thing that we want to do. This is introduction to path learning. It's a distribution over the instances, okay? Over the axis. And I'm assuming that the label is fixed. It's a deterministic F. If I know what, just put the X into the F, and that will be the label. Okay, I'm going to assume that. It's a distribution over the samples. The X's that I get will be random. Depending on S, depending on the sample, I'm going to have a different training loss. Okay? This is D over X. There's over some fixed F that gives you a label. And F of S is what? What was F of S right here? It's the empirical, it's the prediction. It's the ERM. We call that ERM. It's the function that minimizes the training error. F of S. Okay? F of S is the function that we picked for minimizing the training data. You understand what I'm saying? So here is the training data. This is training data. It's random. It's some M samples. Okay? Depending on the M sample that you get, you may get different FS. Okay? So this is the this is the expected loss. Okay? Expected loss. So this, you give me M number of them, I choose my F of S, and then I can get my test error. This is the test error. Okay? For that situation. Test error being less than epsilon. Okay? So this is the probability of picking M samples, getting M random samples, such that the ERM, the test loss of the ERM is less than epsilon. And you want that probability to be less than delta. Everyone? Wow. Who understood and who didn't? So let me hear. S is random. I'm going to say it one more time because this is clear. S is random from training. And based on that, I can, from the hypothesis space, I pick the one that minimizes the training loss. I pick the function that minimizes the training loss. Okay, that's F of S. And this here is the test loss on the F of S that you picked. And I want to find out the probability, that it's less than epsilon. Okay, the test loss on the ERM is less than epsilon. And I want to see what will be the condition such that that is less than delta. The probability, so in words, the probability of test loss on the ERM being less than epsilon, being less than delta. Everyone understand that?
Just regarding the notation, so that D to the M means the probability.
Probability, you can think of probability, okay? And there I'm going to have M samples, that M means M samples, okay? So it's a probability of getting the right training samples so that this is obtained. Do you understand what I'm saying? Okay.
Can I ask a question?
Yes.
Shouldn't we maximize our accuracy?
Okay, forget about accuracy. We're talking about loss. We want to minimize the loss, right? That's the only thing that we define, loss. And I want to I have training samples. Here's the situation. Training sample is coming from some distribution. It's random. I got it. And I have a box full of functions that I can evaluate as a predictor. And I try each one of them to minimize the training loss. And I choose one. That chosen one is called the ERM. And I'm going to denote that as F of S. Okay? And I'm going to evaluate the test loss on F of S. Because that's the objective. Right? And I want that test loss, I want to find the test loss being less than epsilon. Some epsilon, number that you give me. Okay? That's the probability. And I want that probability to be less than delta. What is the condition? You understand what I've said it many, many times, and I'm going really, really, really slow. So, you can consider this thing in two ways, actually. First, you can minimize this. So here, the test loss is defined this way. Probability that the function that you chose, so this was f of s, is different from some ground truth label. What's that probability? Okay, and I'm going to denote that with that for one instance. Okay, and we call this the realizable. So when there is an f, that lies in the hypothesis space that we consider, we call that realizable case. I should be a little bit more. I'm in the realizable case, I'm assuming that f is in H. Okay? The ground truth function is in H. In the general case, there is no deterministic function. We're just going to consider that the data and the label is in some distribution. Is in some distribution. Okay? So what, yes?
그 입실론이 왜 0과 1 사이에 있어야 하나요? 저거는
Oh, okay. So I'm going to assume that the loss function is 0 to 1. Okay? That's a very good question. Okay? Or yeah, I can say that epsilon is unbounded. Okay, it's some positive value, then I don't have to put a condition on f. Okay? Does it make sense? Okay, let me just, the difference between, it's very important that you understand the distance difference. So, x, and we have a label, right? Let's say x was the weight and height. And let's say y is the sex. So male is 1, female is 0. Okay? If I assume this type of situation, 50 kilos, 165, and I had a deterministic function for the label, that means it's always going to be male or female. If there's a deterministic function. Everyone understand that? But in reality, that's not. 50 kilos and 165, it could be male or female, but with different probability. That's this situation. That's this situation. This situation is that there is a deterministic label. So 50 kilos, 165, and there's a deterministic function, you're always male. Okay? Everyone understand this two situation? That's empirical risk minimization. There are some more definitions. Realizability assumption. Here, realizability assumption means that there is some function in the hypothesis space, the function that we're considering is in the hypothesis space, such that the test error is 0. So what does that mean? This means that the f, the deterministic function, is in the hypothesis space. Okay? That's what it means. Please ask questions. You know, it's going to be a little bit more hairy than this. This is basic, easy. Now, IID. I'm going to assume that each of the data that I get is identically distributed. So I get x1, y1, x2, y2, x3, y2. Each one of them come from the same distribution. Okay? And they're independent, meaning that one of the data does not look at the other data and says, what did you get? Oh, so because of that, I'm going to be something else. It's all independent. They're not looking at each other. Okay? I'm assuming that the data is IID, and I think everyone is familiar with IID. Okay? Now, here comes the first packed learning, scenario. Okay? So I want you to look at this picture here. Here, I have drawn a space of m tuple samples. So it's training. So I need to get m data, right? M training data. And each one point represents m training data. Each one of them. Okay? The one that is in these m tuples, the points that are within this m have training loss 0. Can produce 0 training loss. Right over here. Anything outside would have training loss non-zero. Okay? This is the training space. Well, actually, I've written n here, so it's not m samples, but n samples. N, big N. Sorry about this. Here, this represents my hypothesis space. Okay? This is where all my functions, the functions that I'll be considering, will be lying in here. All the functions that will be lying in here. Okay? The functions. Now, so, I've written this, there's HB, and I'm going to call this bad hypothesis space. Bad hypothesis space, because, now let's look. I have, let's say, I get M training data. That's represented by this, right? I have some loss. My loss is defined. 0, 1 loss, let's say, assume. And I have my hypothesis space. And I'm going to, based on this training data, I'm going to try all the points, all the functions here, and I'm going to choose one that minimizes my ERM. And it maps to that. Okay? For each point, so that's this link. Depending on the training sample I have, I'm going to be mapped to a certain function that minimizes the ERM. Oh, but look at this function right here. It's mapping to 2. Why? Because the training law, this one made the training loss 0, and also this one made the training loss 0. It's possible to have 2, okay, on a subset of samples, okay? And one is lying outside the bad, and one is lying within that. Okay? That's the link, how link. Here's the samples, training samples. I have my loss. I'm doing ERM, and so that's the link. Okay? What is bad? Bad is, oh, it seems the bad gives you test error that's greater than epsilon. Test error is, all of this gives you test error. Although the training loss on that data, for that one, let's say, training loss was 0, but the test error is greater than epsilon. Okay? So that's that. Now I'm going to define this M. It's misleading samples. Why is it misleading? It can give you test error, training error 0, but it's mapping to what? A hypothesis with test error greater than epsilon. Okay? Oh, it's based on the training set, it seems to be doing well, but as you map it and you get your f of s, in actuality, it's doing greater than epsilon. Okay? That's misleading. Okay? So, what is misleading? Misleading is all the training samples in the bad hypothesis space. So I'm going to consider all the hypotheses. I'm going to consider all the hypotheses in this space, H bad, that lead to training error equal to 0. That would be misleading, right? I'm going to look at all the bad, which is greater than epsilon, and I'm going to look at all the training samples. I'm going to look at all the training samples that lead to training error equal to 0. Right? It's the union of all that. Right? For each of the hypotheses, what training sample will give you 0 training error? Right? And it's the union of all of them. Everyone understand this? And, okay, so this is another. So that's, I hope everyone understands what this M, what's the space of M, what represents that. Now, look at this. This is the set of all the S's, all the training set that whose ERM, whose all the training set that produces f of s and its test loss is greater than epsilon. Okay? That is going to be a subset of M. Why is that? So we found the misleading. You understand misleading. Training loss is 0, but its test loss is bad, right? Now what about this? It seems like it's saying the same thing. It's a subset. Why is that? Why is that? it represents this red one, for instance. Red one, look. Here the misleading, I'm looking at all the HBs, and ooh, this one gave me training loss equal to 0. Right? So that's certainly in the M set, right? But if I'm given this training set, the training hypothesis that makes it equal to 0 can be this or that. It could be this or that. And if I choose that, then it would not be in here. Do you understand what I'm saying? If I chose this one right here, right? The mapping function could be this. Then it will not satisfy that. So look at this. This is going from here to there. This one is going from here to there. But you can see that for this point, this one can be mapped right over here, which is not HB. Okay, so this is a subset of that. It's a very important point. Okay. You didn't think statistical learning was going to be like this, but we're going to be doing things like this for a couple of lectures. This is the foundation for learning, okay? So now, given the accuracy, 1 minus delta, confidence and accuracy, okay? And our goal is to do this. The probability of the test loss being less than epsilon, I want that to be less than delta. Okay? What is that? What is the condition for this? Is this a good condition? Is this something you would like? First of all, I want to say this. Is this a condition that you would like? Epsilon delta is something that you can choose. Any number. Is this a condition that you would like? Is this a good condition? Tell me. 어떻게 생각해?
Yes.
Who said that? Oh. Yeah. What is this? This is certainly a good condition. I want my test error on the f of s that I found to be not large. It's bounded about epsilon with certain probability. Okay? This is good. Okay? And what is the condition for this? It comes from this. This is from the previous slide, right? That this set was a subset of M. Okay? So I'm going to start here. I'm going to put a probability on both sides. Probability of this event is going to be less than the probability of M. Everyone agree with that, right? There's two sets. This one is a subset of this one. So I'm going to put a probability and a probability, and then if you put a probability, then you get this. Okay? So on the right-hand side, I'm going to work with the right-hand side. Probability of the union of this set. I'm going to take out the union. Okay? Union, I can I can bound this thing by the sum of each of the probabilities. What do I mean by this? Okay, the probability of A and B, the probability of union of A and B is going to be less than the probability of the sum of each one of them. right? And that's what I've done right here. Okay? That's what I've done here. And what is the probability, what's dm? It's probability of over m samples, or m tuples, right? So I'm going to put, so m samples. So that can be represented as the product of each one of them. Product of each sample, instance. How many instances do I have here in the set? M. Each one are identically IID. So it can be represented as a product like that. Right? This part, summation comes down, product. What is this probability? So this, it's 1 minus the test loss. Very good. Excellent. Test loss. So, what is that? What is this right here? We said that this one is going to be, this is the probability, represents this probability. We said that this is each one of them in the condition to be less than epsilon, right? So it's 1 minus epsilon. This one is less, it's bounded above by epsilon, because this one is bounded by epsilon. Okay? And each of them are same, so I put a product like that. Okay? And I find that 1 minus epsilon is less than e to the minus epsilon. And this is an example. 1 minus epsilon is always below e to the minus epsilon. So bounded. Okay? So summation over this function, how many functions I have in my bad hypothesis space, e to the minus n. So how many samples do I have? Let's just say that's represented by the cardinality of the bad. Cardinality. What does this mean? This may be a new notation for some of you. What do I mean by the cardinal absolute? It looks like an absolute value of the space. What do I mean by this? Number of the hypothesis space in the bad. Right. Very good. Very good. Very good. Okay. Each the min. But certainly that the number of hypotheses is less than the total hypotheses that I've considered, right? Right there. So I can bound that up like that. Right? And I want this number to be less than delta. Yes?
서브 방향이 좀 잘못된 것 같은데.
어디?
그 증명에서 시작할 때는 로스 펑션이 엡실론보다 큰 걸로 시작.
아, 됐어. 여기는 엡실론이 큰 걸로 생겼어. 죄송.
그 자체도
아니,
엡실론보다 큰 걸로 가야 되나?
아, 여기는 여기서 그래서 yeah, right over here. So that's why if this is so this is the condition, right? So if this is greater than epsilon, then this one is less than. 그러면 되는 거죠.
우리의 그 볼 자체도 로스가 작은 게 좋은
아,
건데 확률을 작게 만드는 게 아니라 로스가
So,
큰 확률이
oh yeah, yeah. So it's the other way around. Okay, so this is. Thank you. This is equivalent to dm. 아, 저 다 따라하고 있다는. 너무 훌륭하네. F of s. Yeah, very good. This is less than epsilon, meaning that this is greater than 1 minus delta. This is equivalent to that, right? This and this are equivalent, right? So it should be greater. Sorry about this. Sorry about that. Then I don't have any problems. You're very right. Thank you.
전 슬라이드로 똑같이 붙이면 돼요.
전 슬라이드도 마찬가지인가요? 전 슬라이드
그전
어디
전
전전인가? 네, 요거 죄송합니다. 오케이. So this means that, okay, let me just say it again. The test loss being greater than epsilon is, if I choose my delta to be very small, let's say 0.1, any number of it, 1%, test loss being greater than some epsilon is bounded above by some small number. So it's very unlikely that the test loss is greater than epsilon. I can bound it that way, right? That makes sense. Thank you, thank you. I like feedbacks like that because I know that you are following the lecture and understanding this. That's good. Thank you. So, this is correct. This is correct. Okay? So what do we... So this is the relationship I have. This is the relationship. This is the number of hypotheses that I'm considering. This is the number of hypotheses that I'm considering. Okay? M is the number of training samples. And epsilon and delta is the number that you give me. Now what can I do with that? What can I do with that? I can rearrange it such that M is the subject. It looks like this. Okay? I could rearrange it so that M is a subject. And I get this. What does that mean? What does that mean? What does that mean? So in order to have this, so what do you mean? I choose my ERM. These two are equivalent, by the way. I choose my ERM and and I look at the test loss being less than epsilon. What? And this is the probability of the samples such that this condition happens. And I want that probability to be 1 minus delta. And usually delta is small number. Then that probability is very, very high. That this happens with high probability. This happens with high probability. Here in this case, being over something, a very low probability. Okay? I wanted this, and I got this. What does this mean?
have at least that number of samples to give a probability.
I need to have this many training samples in order to obtain this. Yes. So the number of samples, depending I have more and more samples, I can get very good test loss performance. I can guarantee certain test loss. So let's have a look. Let's have a look. So if I have epsilon very small, smaller epsilon, so I'm considering the test loss of Fs to be small. Epsilon really small. Does that mean I need more samples? If epsilon gets smaller and smaller, it's a much stringent condition, right? And you see that epsilon is in the denominator, which means that I need more samples for that. Okay? Let's say if I have my delta smaller, so that I want this condition to happen with high probability. As delta gets smaller, I want this probability to be very, very high. Then, do I need more samples? Yes, that's what that's saying. That's what it's saying. Okay?
Professor,
Yes.
this might be a bit out of context, but you assume that the hypothesis space is finite. That's why we have these kind of expressions.
Yes.
This continuous.
Also very good. Okay, thank you for it. So I've assumed here the hypothesis space is finite. But, of course, you're going to say something?
If it's infinite operation.
Yes. Then we'll do something else. Okay? That leads to VC theory. Okay? Or what we can do is we can sort of discretize. Even though it's linear function, let's say, linear function it's an infinite space, right? But the gradient and the y-intercept, if you want to program, it's going to be in what? It's a floating point, right? How many bits? Maybe 64 bits. Yeah? 2 to the 64, then it's going to be finite, right? You can think of it that way. Wow. To explain that, it took me 51 minutes. Okay, so now, so for any labeling function, I've assumed here that there was a labeling function. Okay, in all of this, the labeling function, and there's also a distribution of the data. And I've made this realizability assumption. What do I mean by this? This labeling function is in the hypothesis space. So I get zero training loss. Zero training loss. Okay? So for every ERM, this is true. Okay? And I need to have sufficiently large M for this to be true. And this is correctly. So this is not the same as that, for instance. Right? It has to be that. It has to be that. Greater than. Okay. So I have to make some modification. Thank you. Now, so this having a labeling function, it's we don't have that in reality. As I said, male and female, 50 kilos, 165, always being female, that's ridiculous, right? We want to consider a more general case, okay? And for that, well, before I do that, okay, so I want to first define, before I do that, I'm jumping myself, I'm going ahead. Now I want to talk about packed learning. Okay, now I have to define what packed learning was. Packed learning. And I want to, it's a characteristic of a hypothesis. H. It's a hypothesis. Okay, certain hypotheses. It's and we say that it's packed learnable. It's packed learnable if there exists a function. A function that is two variables that's between 0 and 1 and produces a natural number. What does that mean? We're talking about the number of samples, okay, which is a function of epsilon and delta. This is what it's talking about right here. There exists a function that's a function of epsilon and delta, which is a value between 0 and 1 that maps to a natural number. Gives you samples, 5 or 50 or million samples. There is a function. An example would be this. right here at the bottom. It's pack learnable if there is some function that's a function of some variable that's between 0 and 1, that's like epsilon delta. It gives you some number and a learning algorithm with the following properties. So you have some number of samples, if you some number of samples. For every epsilon and delta between 0 and 1, and every distribution over x, only the data, and for every labeling function, this deterministic function, if the realizability assumption holds. What does that mean by realizability assumption? It means that this function is in the hypothesis space. So you have hypothesis space, you have some distribution, you have this label. Then when running the learning algorithm, if you have more samples than this, generated by D, labeled by F, the algorithm returns a hypothesis F theta with probability of 1 minus delta. The test loss is going to be less than epsilon. And that's what we did right here. That's what we proved. Okay? That's pack learnable. It's a characteristic of the hypothesis. Okay? It's long, but and here, every finite hypothesis. This is the case that we could ask. More hypothesis. The M of H was this. This is what we derived. This is what we derived. This is the MH. If we have more samples than that, then the probability of our test loss being less than epsilon, the probability of test loss being epsilon is going to be least, it's going to be greater than 1 minus delta. It's going to be greater than 1 minus delta. Okay? And this is Professor Valiant, a Harvard professor, and because of this, he won the Turing Award, this formulation. What is this? What is the significance of this? What is the significance of this? Machine learning, by pack learning, does not only consider just training loss, doing well on the training loss. It's thinking about test loss and putting a guarantee on how well you're going to do on test loss, on the real world, in the field. So if I have certain training data of certain size, and I have a hypothesis space, and I find a function that does well on this training sample. This function, if I take it outside in the real world, it's going to perform like that. It's going to perform. It's going to have a test error less than epsilon. Which is very, very significant. Okay? So that's pattern. That's pack learning. Now, let's consider the case where you don't have a deterministic function. Okay? Because it doesn't happen in that way. Okay? So here, and that's called the agnostic pack learning. And in agnostic pack learning, it's exactly the same words, but there is no labeling function. The D is not over just the X, but it's over the product space. It's over the joint probability of data and the target weight. Okay, that is agnostic pack. Okay. Okay, so here in this case, the test loss. Actually, this maybe it's not exactly correct. I should have a probability of. I think this LD. LD is defined this way. Right here. Let me use. I want to. LD is right here. I've defined it right in the very beginning. LD is the probability of my predictor not being equal to ground truth over the joint probability. Over the joint probability. Okay. And, okay, exactly the same words. Now, instead of guaranteeing some bound on the test loss, here the bound is a little bit different. The test loss of some function, or actually fs, some function is going to be less than, there's some function f theta such that this happens. The minimum of the test loss of all the functions that you've considered. Okay? So I can only consider all the functions that are in the hypothesis space. Okay? I put each one of them and I can look at the one that minimizes the test loss. Okay? That test loss plus some epsilon. Okay? This is very hard to achieve right here. Plus epsilon. Okay? So it returns a hypothesis, agnostic pack learnable. If I have samples greater than some MH, if my training set is greater than MH, then the learning algorithm can return a hypothesis whose whose test loss is the minimum test loss achievable by the hypothesis plus some epsilon. And this happens with probability of at least 1 minus delta. So this is good. This is good. Okay? So you give me some epsilon, and you give me some delta. Okay? So let's say I want this to happen with certainty. That means what? Delta has to be what? If I want this to happen with certainty, delta has to be what? Small, right? And so delta small, and I want my test loss, the function that I got, the test loss of the function that I got, to be almost optimal. That means what? Epsilon has to be what? Also small. Both epsilon has to be small, right? If these two, then there's going to be some function that tells you how much samples I need, at least so much samples, okay, which is a function of epsilon and delta. If I have samples over that, more than that, then this is going to be guaranteed. That this is going to happen with that problem. 네.
저는 리얼라이저비리티 assumption 안 쓴 거.
여기서 realize no. So this here in this case, LD FS, sorry, it's not 0. So there is no function that is, there's no labeling function. There's no labeling function. So realizability means that there is a labeling function that's in the hypothesis space, and if I choose my f of s to be f, then this is going to happen, right? This one, not in this case.
So there is no labeling function for this case.
No labeling function. There's no labeling function. There's no deterministic labeling function in this case. Okay? Okay, now we're going to go and try to find what this MH is. That's our target. But I'm going to assume that the hypothesis space is finite. Okay? That's my next task. Before I do that, I'm going to give you some definition. Epsilon representative. What does that mean? If a training set is called epsilon representative, then this is true. For any function in the hypothesis space, the training loss and the test loss is different, less than epsilon. So this is good. This is good. Okay? If a training sample, this is just the definition. If the training set, is called, if it's epsilon representative, then the difference between the training loss and the test loss is less than epsilon. Okay, that's the definition. This is a good training set. Now, we learned that ERM is a path learner. Now, assume S is epsilon over 2 representative. Half the epsilon representative, or 2 over epsilon representative, or epsilon over 2. In English, you say this first, and then that. In Korean, you say that and that. So, okay, well, it is half of epsilon representative with respect to domain Z. Z now represents the training and the label. It's the product space of the training and the label, okay? And we have some hypotheses, loss function and distribution, okay? S is that. Then the f of s, now f of s represents ERM for that. Okay, f of s represents ERM with respect to that. Then this happens. So if I'm given, if my training set is this, then the ERM is agnostic pack. Is agnostic pack. Okay? Why is that? I can prove this in one line. Here it is. So because it's epsilon over 2 pack, epsilon over 2, S is epsilon over 2 representative, the difference between the test loss of my ERM and the training loss is going to be bounded above by epsilon over 2. Right? Where does this come from? The definition of epsilon over 2 representative. right? That's the definition. Now, because I can put in anything, I can put in fs and I can get that. Now, f of s is the function that minimizes the training loss, right? So if I put in some other function, this loss is gonna be greater than that loss, because that's the definition of f of s. F of s was going to be the one that minimizes this. So I get that. So I get this, right? Put that right there. Now, f of s and LD, I put the same function. Because s is epsilon over 2, I could do that. This is bounded above by this plus that. Right? So I got epsilon over 2. So I have that. Okay? So if my training sample is epsilon over 2, or 2 epsilon representative, then ERM is agnostic pack learnable. And you may say, what? Why are we talking about ERM? What is the significance? So in machine learning situation, you're given training data. And I have a hypothesis space that I'm considering. And I choose my function that minimizes the training error. Okay, that's what we usually do, right? I have my training data and I try to minimize the error on that. Well, the loss on that. How well is that function going to perform outside in the real world? I need to have some kind of a guarantee. Right? And I can get that guarantee only if there were enough training samples that made my FMS. This is very, very significant, right? You get your F of S, how well is that going to perform? And then let's say my customer wants certain guarantee. I want this to perform with this accuracy. In order to have that guarantee, that accuracy, I need to have lots and lots of samples. Okay? So it's 212. Actually, I was going to finish this slide, but I think I'm going to leave it until next week. Okay? So it's 212. So you should go to the next class. Any questions? Yes.
So we can choose like different functions, and for different functions we will have like different number of samples that we need.
No. So I have a hypothesis space. Okay, I have to define that. Okay, there's a bunch of functions there, right? I have a hypothesis space. I have a hypothesis space, all the functions, linear functions, all the linear functions, all the quadratic, or it may be all the mapping that my deep learning architectures can do. That's also a function that's in the hypothesis space, right? For that hypothesis, I need to have, so that's the number, I need to have, and epsilon and delta, I need to have a certain number of training samples.
But what if hypothesis space is uncertain?
Uncertain? What do you mean by uncertain?
For example, you don't know that it's linear or
You have, that's your choice. Of course you know. Of course you know. What function are you going to use as a predictor? What function are you going to use as a predictor? That's your choice. And that's your choice. That's inductive bias. You have to make the right choice. You have to select the right choice of functions for the task that you have. Okay, more questions? Okay, if there's no questions, I guess that's it. I'll see you next week. And have a nice Thanksgiving.